Hi there, welcome to lecture 10 of Machine Learning from Data. We're going to be talking about nonlinear transforms, which are a very simple but powerful add-on to linear models. Okay. Now first, let's recap where we were from last time. Okay, so we've talked about the linear model, and specifically the linear signal, which is W transpose X. The linearity in W is what we really cared about when we meant linear, and that's what makes the algorithms go. The linearity in X is also important. That's what gives us the linear separator. Okay, and today we're gonna discuss how we can sort of keep the linearity in W so that all our algorithms will continue to go, and somehow relax the need for linearity in X and I'll allow more complicated separators. Okay, but that's a little preview of what's to come. With respect to the linear model, we showed that we can address different kinds of problems by taking this linear signal and transforming it. You apply the sign to get classification. You don't do anything to it if you're doing regression. And if you're doing a probability prediction or logistic regression, you apply that convenient sigmoid that we talked about last time. Okay, and each of these problems, approve or deny credit, that's classification, comes with a learning model, the perceptron, and an error that you try to minimize on the data, the classification error, and algorithms for picking the hypothesis, the PLA or the pocket or regression for classification and so on. If instead you're trying to predict the amount of credit, then we're talking about regression, and we're minimizing the squared error, and we describe the pseudo-inverse single-step algorithm that gets you to the best hypothesis. Okay, if instead you want to predict a probability, so we're talking about logistic regression. Okay, and here the appropriate error which has a probability interpretation is the cross entropy error. So you grade the hypotheses in your hypothesis at the linear model using the cross entropy error, and we discuss gradient descent or stochastic gradient descent as an efficient method for picking a hypothesis from the hypothesis set, i.e. the linear model with the sigmoid applied to it. So picking one of those hypotheses that minimizes the cross entropy error. We can minimize the cross entropy error pretty efficiently because the error function that we derive, this cross entropy error, is very well behaved. It's not only having this probabilistic interpretation, but it is convex, so it has a single global minimum. Okay, now today we're going to continue talking about the in-sample error, and I will remind you, okay, in figure A is one, there are different ways in which non-separable data might present. Okay, now in A, I'm showing you the situation where you have basically linearly separable data, but a few outliers. So there's red X and there's blue circle. Okay, so you'd like to keep the linear model, but tolerate outliers. Okay? And that's what we discussed when we talked about the perceptron with the pocket algorithm, so tolerating outliers or regression for classification. Okay, so today we're going to be illustrating mostly with respect to classification, but everything we say today can be applied to regression and logistic regression. Now, on the right, I'm showing you a different kind of non-separability. Okay, on the right, it's not the case that you can find a linear separator that more or less works with a few errors. Okay, no matter where you put your linear separator on the right, you're going to make a lot of errors. So, for example, think of something like a diagonal linear separator. It's going to get approximately half the blue wrong and approximately half the red wrong, as opposed to a few outlier mistakes. Okay, so on the right, we need something fundamentally different from just an algorithm that can tolerate errors. Okay? And if you think about it, when you look at these blue circles, you see, they somewhat form like a region in the middle. So rather than separating blue from red with a line, maybe we can separate with something like a circle or an ellipse. And that's a totally different model than the linear model. Okay? What I'm going to show you today is that we can essentially keep all the technology of the linear model and solve the problem on the right and get circles. Okay? And the technique that we're going to introduce is the technique of the nonlinear feature transform. So essentially, we're going to transform the X space. We're going to transform the features so that the linear model can still solve the problem. So we can still use all our old favorite algorithms, PLA or pocket, regression for classification, regression for regression, or gradient descent to minimize the cross entropy error. Okay, and so that's the topic of today, nonlinear transform. And let's go to the board. Okay, so let me show you the basic idea of the nonlinear transform through an example. And let's go back to our credit approval application. Okay, and I'm going to put income here. Okay, I, and years in residence Y. Let me put that on this axis. And let's think about credit approval. So for a particular number of years in residence, you might need a certain income above which you will be approved. As I increase your years in residence, that threshold is going to drop. Okay. But now, if you think about it, and this is a phenomenon that happens very often in the real world, it's what's called saturation. As you have more and more years in residence, I don't care. I don't care about the difference between 25 years and 26 and 30 and 40. Once you've been in residence for a long time, you're stable. Okay. So this threshold above which you're going to get credit is going to flatten out. Okay. And the same thing on the other end. I don't care about the difference between 6 months and 5 months and 3 months and 2 months. Once you have not been in residence for a long time, you're unstable. So this threshold is also going to saturate and flatten out. Okay? And so, the classification boundary looks like that, and this is going to be your plus region, and this is going to be your minus region. Okay? So, and when we think about this problem, we see that the linear model is not right, except it's not really that the linear model is not right, it's just that our feature y that we are capturing is not the right feature. So we should, when we sit down and think about the problem, we should realize that the real world has saturation phenomena. And so when we collect this feature y, we should incorporate the saturation phenomenon in the feature y. Okay? What that means is I'm going to take my feature y, years in residence, and transform it to, let's say, a new feature z. And how does this transform look? Okay? What it should do is it should take, y, okay, and when the values of y are very, very large, they should all map to the same value of z. So it should look something like this, and then it can become linear. But again, when y gets very, very small, now we don't care, and so it should saturate on the other side as well. Okay, so this is an example of a transform of a feature that incorporates saturation of the feature. It says once the feature gets above a certain value, it's just high, and once it gets below a certain value, it's just low. Okay? What will that do to this decision problem, this classification problem? So let's see. Okay, here's what it will do. Okay. It's basically what's happening is these y values all get bunched up, and they all map to the same z value. So if I look at z on this axis and the income I, so all these y, the z values corresponding to all of these guys is some value. Okay. The z value corresponding to all of these guys is some other value, and then in between it's linear. Z linearly interpolates in between. So this boundary becomes that. And what's the plus side? This is the plus side. Okay, and this is the minus side. And we see now the linear model perfectly works for this classification problem. And that's what I said earlier, and I've been saying it many times. If you can't solve the problem with the linear model, odds are you haven't thought about the problem yet. Okay? So if you think about saturation phenomena and incorporate them into your features, now all of a sudden the linear model is appropriate. Okay? And that basic idea of transforming your features so that the linear model now becomes appropriate is exactly what the nonlinear feature transform does. Okay? So let's work through the mechanics of the nonlinear feature transform. Okay. And you will see that it's basically the same idea, and it's not a huge rocket science except for the few rules of thumb that we're going to require. Okay. So the starting point is the original data, just like the problem we had before. Okay, so let's call this the mechanics of nonlinear transform. Okay, so you start with your original data, and now think back to the slides. You had this inherently non-separable data set, okay, which is different from the one where the data looks essentially linearly separable, a few outliers, and so you want to tolerate error. When you're dealing with the essentially nonlinear data, it's not that you want to tolerate error in the linear model. You need a completely new model. Okay, so I'm going to illustrate that data. Okay, think of, so I have two features. Let's call them x1 and x2. Okay, and I have, so think of this as 0. So I'll just draw the axis here. Okay, this is 0, and that's 0. Okay, and I will draw my data points. Okay, a bunch of data points. Okay, and we have our x guys, our red guys. Maybe something like that. Okay. So you can think about this as x1, x2, okay, and my feature, my augmented feature x, okay, is 1, x1, x2. Okay, so that's the standard setup. And okay, of course, if we look at this data, we look and say, oh, the linear model is not good. And so one of two things, either you need to tolerate error or you've gotten the wrong features, and we need to transform the features. We need to transform this X guy. Okay. Now, the important message is that you cannot look at the data to decide that. Okay, and we'll discuss this a little bit later. So you have to decide whether or not you're going to use the nonlinear feature transform before you look at the data. Okay? So what you're going to do is you're going to transform this using what we call a nonlinear feature transform. Let's use the Greek symbol phi. Okay, and in this case, just to make things easy to visualize, we're going to transform it to a transformed feature z. We'll call that z. Typically, x is the original feature, z is the transform feature, which I will write as 1, z1, z2. Okay, so I'm going to transform also to 2 dimensions. Okay, so z1 and z2. That's just so that things are easy to visualize. Now, the transformation need not match the dimensions of the original feature transform. In fact, so for example, with the digits data, we took 256 dimensions of original features, if you remember, and we constructed intensity and symmetry, which takes those 256 dimensions down to 2. Okay? So that's an example where the dimensionality of the original feature is much bigger than the dimensionality of the transformed feature. Now, in that case, we did that because we had to. We have a small amount of data, so we need to, lower the dimension so that we can get the link from E into E out. Okay. Here, we're doing it because, in our original 2-dimensional space, we're not going to be able to get E in low. How do we know that? By looking at the data? No. Just, by thinking about the problem, thinking about saturation phenomena, etc., etc. Okay. So we transform to this new feature, and I will write this new feature as z1, z2. And now each of these coordinates of the new feature can be functions of the original feature. Okay? So 2 points. The first point is the dimensions in the new feature can be larger or smaller or equal to the original feature. And each new feature, okay, can be a function of the entire original feature. So we will say that this is equal to, 1. That's the augmented one. Okay. And phi of x, phi 1 of x, phi 2 of x. Okay. So you could have more than, so the transformed feature z1 can involve both x1 and x2. The transformed feature z2 can involve both x1, x2, and if there's a z3, a z4, and so on. Okay. All right. And I'm going to choose for this particular transform, just to illustrate, I'm going to choose the transform, so I'm going to choose z1 equals to x1 squared and z2 equals to x2 squared. So phi 1 of x happens to only depend on x1, it's x1 squared. Phi 2 of x happens to only depend on x2, it's x2 squared. Okay, so let's see what happens to my data. Okay, so in my new feature space, okay, now why I chose that transform is illustrative, okay, because I want to show you what's going to happen to the data. Okay, so in this new space, observe that my new features are x1 squared and x2 squared. So what happens to the sum of x1? What is x1 squared plus x2 squared? x1 squared plus x2 squared, so z1 plus z2, z1 plus z2 is exactly x1 squared plus x2 squared, which is equal to r squared. It's equal to the distance from the data point to the origin in my original space. Okay? And so what it means is that, points that are close to the origin here will have a small value of z1 plus z2, and points which are far away will have a large value of z1 plus z2. Okay, so imagine that I consider I define something. So z1 plus z2 is a line. Z1 plus z2 is basically z1 plus z2 equals some constant. Our lines going in this direction. Okay, and the red points will be above that some threshold, and the blue points are all close, so they'll be below. So these blue points will all map somewhere here. Okay. And these red points will all map, somewhere here. Okay. Look at that. So what did my transform accomplish? It accomplished that my blue points and my red points in my new space, so we will call this the original X space X, and we will call this the transformed Z space Z, and I'm trying to write these as script capitals, but you know, you get the idea. So this is my transformed space. In my transformed space, the blue and red are easy to separate with a line. So I pick a line. So my next step, so this is, you can think of this as the first step, okay, original data. The second step, transformed data. The idea behind transforming the data is that in this new space, the data can be separated by a line, or in general, if it's more than 2 dimensions, a hyperplane. Okay? So in this transformed space, okay, I can separate with a line. So here's my data. Okay, dot. Ah, beautiful. Okay. And now I can find a line that separates. Okay. How do I find this line? Well, I use whatever algorithm I was going to plan on using in the original space, but I just use it in my Z space. So I could use the PLA with Z data points, okay, to find this separating line. Let me call this G tilde of Z. Okay, so now tilde is just to indicate that it's something else. It's not G, the final hypothesis. Okay, and it depends on Z. So it takes in, so this is Z1, this is Z2. So it takes in Z1, Z2, and of course the augmented one. And you know, if you're above this line, it outputs +1. If you're -1, if you're below the line, it outputs +1. Okay, and G tilde of Z is exactly equal to the sign of W tilde transpose Z. Okay, because it's a linear model in my transformed space. So that's very important to understand that. Okay. And in order to get this W tilde, all I have to do is run the linear model in my transformed space. Now, okay, essentially I'm done. I've got my classifier, except, you know, that your client gave you data in the X space. Okay. So as far as the client is concerned, they don't care what you do. So I'm going to put this behind a curtain. Think of this as a black box. Okay. You have done this behind the scenes because, you know, you sensed, you thought that, you know, the data is not going to be linearly separable without looking at the data. And so you invented this feature transform, and miraculously that feature transform succeeded in getting E in 0. That was the whole goal. And you managed to keep the dimensions down to 2. And so you've got your E in versus E out. Okay. But, okay, when your client needs to use your final hypothesis, okay, they don't know anything about this Z space. So the test point comes, okay, so test point comes, X1, let me call it star, X2 star. The test point comes, okay, and it's in the original space. Okay, so how does the client use this classifier that you have built in this weird new space? How does he use that? How does he deploy that in the real world, which is his original space? He's only going to measure, you know, income and age. Okay, but you've done some weird thing to get 2 new features, and you've done some magic here and gotten a separator. But when he needs to use your model, he's going to come with income and age. Okay, no problem. You just need to invert this into this world. Okay, it's not easy to do that inversion, especially if this nonlinear transform is going to have a mismatch of dimensions. No problem. You do exactly the opposite. You tell the client, you know, when you get a new point, here's what you're going to do. You're going to give me the new point. Here's what I'm going to do. I'm going to take this new point, okay, and I'm going to figure out what its position is in my new space. And how do I do that? I can just run phi. Okay, so my new point, let's call it X now. Okay. Let's just call it X generically, even though technically it's the test point on which I'm being deployed. My new point X is going to produce phi of X here. Okay, and now I pump this point into this space. Okay, and I see, are you on this side of the line or on that side of the line? If you're on this side, I'm going to say you're blue. If you're on that side, I'm going to say you're red. Okay. Now, hypothetically, I can play that game with all the points in this space. I don't need to wait for the new point. Okay? So I can hypothetically play that game with all the points in this space. And what you will find is that, all the points that are within some region here, will all get mapped into this point, into this region, and be classified as blue, as +1. So this entire region will ultimately get classified as +1, and anything outside that region, when you implement this nonlinear transform, will be pumped into the red region and be classified as red. And so, this region will be classified as red. Okay? And so, in effect, by doing this process of taking a point from here, looking at where it will land here, and classifying in this space, in effect, I have implemented a boundary between red and blue, which is nonlinear. In this case, something like an ellipse or a circle. Wow. Okay. Look at that. Beautiful. Okay. So this is the effective boundary my client sees. And it's non-linear. And of course, I'm not going to tell them that there's this huge black box machinery behind the scenes here, and actually they're effectively just using a linear model in some, more sophisticated space. I'm not going to tell them that. I'm just going to say, listen, I'm going to give you a feature transform, and when you need to classify, you run your feature transform, okay, and then you run my model in that space. And then when they look at what's happening, when they see the test points, they'll find that all these guys are red and all these guys are blue. And wow, it looks like you did something very sophisticated, not just plain old linear. And so again, I will reiterate. We are just using the linear model behind closed doors. Okay, and the only thing I've added on top of this linear model is this feature transform, showing you the power of the linear model. Okay, showing you the power of the linear model. Now, you will note that in this whole process, the only thing I transform is the features. x1, x2 goes to z1, z2. The color of the points stayed the same. Okay? So let me summarize these mechanics. Okay? The general feature transform. Let me summarize these mechanics. The general feature transform. So, I'll separate out in my summary what's going on in the x space from what's going on in the z space. Okay, so this is the x space, and this is the z space. Okay, and if you were to sort of encapsulate the entire process of pumping up your test point into phi of the test point and then classifying, what are you effectively doing? You're setting z equal to phi of x in this formula, okay? But now you're implementing a classifier in the original space, so we can actually call that our final hypothesis. G of x is equal to g tilde of phi of x, which is just the sign of phi of x transpose of w tilde transpose phi of x. Okay, and that'll appear in this summary. Okay, so in your x space, you have the input, x, which is augmented to 1, x1 up to xd. Okay, so now I'm generalizing. This is the picture for 2 dimensions, 2 dimensions to 2 dimensions, but now let's see what happens in d dimensions. Okay, and in your z space, you get z is equal to phi of x, which is equal to 1, phi 1 of x, phi 2 of x. This is the entire x. Phi 1 need not just depend on x1. It can depend on the entire x. And phi 3 of x, and so on. And you can have any number of dimensions here. Okay, so we'll call the dimensions here phi d tilde of x. So let me just use the convention that if something is in the z space, I will put a tilde on it. So the dimension in the x space is d, the dimension in the z space is d tilde. Okay. Now, let's look at your data. Your data. in your X space, and that's the data your client gave you. Okay? In your X space, it's X1, in the X values are X1, X2, X3, up to Xn, and corresponding to those X values are Y1, Y2, Y3, up to Yn. Now I will emphasize that even though this entire discussion was for classification in which the Y's are plus or minus 1, the Y's can be anything. Okay, they can be plus or minus 1, they can be real numbers, whatever they are. Okay, so the discussion applies to all the three problems we've discussed so far: classification, regression, logistic regression. Okay, and you'll see why. Okay, so now what happens in the Z space? Each of these X inputs, each of these examples Xi gets transformed to the corresponding Zi. So you're going to have Z1, Z2, Z3 up to Zn, where Zi is equal to phi of Xi. What happens to the Y values? Nothing. They stay the same. So the Y values in your data do not change. Okay, so you get Y1, Y2, Y3, up to Yn. So this is your data in your Z space. This is the original data in your X space. Okay. Now, we're going to implement the linear model in the Z space. We're going to implement the model H of Z is equal to sine of W tilde transpose Z. So why W tilde transpose? Tilde, because we're in the Z space. Okay? So you need to fit this model to this data. That's all that's going on. And so you use your favorite model for the linear, for your favorite algorithm for the linear model. If you're doing classification, it's PLA or Pocket or regression for classification, and we'll see other kinds of algorithms for classification. If you're doing regression, it's the pseudo-inverse algorithm. If you're doing logistic regression, you minimize the cross-entropy error using gradient descent. Whatever your favorite algorithm is for the linear model and the type of problem you're doing, you use that model and obtain the weights W tilde, let's call it lin. Okay, so it's the weights for the linear model. Tilde means in my Z space. Okay, and so my final classifier, my final hypothesis in my Z space is G tilde of Z. G tilde, because it's in my Z space, is equal to sine of W lin tilde transpose Z. Okay. Now let's see what's going on in the X space. In the X space, what is the type of, what are my weights? So I get weights W lin equals, okay, let's see, how many weights do I have? I'm going to have weights, I'm going to have W tilde 0, W tilde 1, all the way to W tilde D tilde. Okay, so there are D tilde plus 1 weights. Okay, now, what are my weights in my X space? This is important. There aren't any. There are no weights in the X space. So you're running the linear model under the hood in the Z space and in the Z space only. You're not running it anywhere else. Okay? So then I need to classify in my X space. So I need to have a final hypothesis in my X space. And the final hypothesis in my X space is actually well defined. G of X, okay, is equal to G tilde of phi of X, which is equal to sine of W lin tilde transpose phi of X. This guy is what we were calling Z. Okay, this guy is what we were calling Z. And this final hypothesis corresponds exactly to this process. So if you give me X, I first compute phi of X. That pumps that data point into my new space. I first compute phi of X, and then I apply this classifier. I.e., I decide whether my point that the test point got transformed to is on this side of the line or that side of the line. Hyperplane in general. And that's it. That's how incredibly simple the feature transform is. But once you have the feature transform with the linear model, you can essentially do anything. Okay? And by choosing a suitable feature transform now, we can certainly get E in close to 0. So we are addressing the E in equals 0 issue here with the nonlinear feature transform. That's explicitly what we're using it to address right now. Okay? And then the obvious question is, what about E in versus E out? What about E in versus E out? So let's erase and let's come back and talk about E in versus E out for this nonlinear feature transform. Okay, so let's talk about generalization and some practical issues like how do you choose this nonlinear feature transform. Okay, so first of all, just to summarize, in your X space, you have X is in 1 cross R to the D, okay, and in your Z space, Z is in 1 cross R to the D tilde. Okay. Now, if you ran a linear model in this space, your VC dimension dVC would be, equal to D plus 1, and you prove this. Now, there's no difference. You've just taken your data, okay, and just, bloated or shrunk the number of dimensions, maybe kept them the same. Okay, so your new number of dimensions is D tilde. Okay, so your VC dimension here, dVC, let's call it dVC tilde, is equal to D tilde plus 1. Okay, and it's the same theory, it's the linear model, it's the perceptron, so we have control. So the error bar, so E out, will be less equal to E in for G, okay, plus, order of the square root of D tilde over N log N. Okay, so because it's a linear model, but in a higher dimensional space, you have the link between E in and E out, and the error bar is related to the dimension of this space. Okay, and that raises the question, so what should you pick for the dimension of that space? Okay, so what should D tilde be? Okay. And the obvious answer is go to the lowest dimension space that you can while still getting E in, let's say, close to 0. Why? Because if you're in the lowest dimension space D tilde that you can, now you've got an E in close to 0, okay, and you've got the tightest link that you could possibly have asked for if you've gone to the lowest possible D tilde. Okay, so choose D tilde small gives better E in, E out approximately equal to E in. Okay, so smaller D tilde accomplishes the first step of learning more efficiently. Okay, and this leads us to the issue of, well, picking D tilde amounts to picking the nonlinear transform. And in general, there are many ways to pick the nonlinear transform. So in general, there are many ways to pick phi. And, what's illustrated here, okay, so, we have our data, okay, and let's get some red and blue markers. Okay, so we have our data with, blues, okay, and reds around, okay, and that's the top graph over there, okay, and, the first transform that goes down, which basically goes to Z1 equals X1 squared, Z2 equals X2 squared. That's the one we've been discussing all along. And on the left, we show another transform, which is, just take Z2 equals X2, Z1 equals X1 plus, that's something like 0.6 squared. Okay, and, this guy succeeds in separating the data by putting the, the reds on one side and the blues on the other side here. Okay. And this transform succeeds in separating the data by putting the reds sort of on the right and the blues on the left. Okay? And so in both cases, here you can separate with this line, here you can separate with this line. And as you can see, there are many different feature transforms that one could choose, which accomplish the goal of getting E in small, and we want to choose the one with the smallest dVC tilde. Okay, so now, when you think about it and look at this data and you say, well, that's, interesting, because, here's a circle, and it turns out that the equation of this circle is x1 squared plus x2 squared equals 6. Okay, so what about if I just take my data? So what about if I define a feature transform to one dimension? Okay, just one dimension where, my one dimension Z1 is equal to x1 squared plus x2 squared minus 6. So literally, if this is 0, okay, it takes all my blue points and takes them to less than 0, because this is less in this region. You're less than this value. Okay, so when you compute x1 squared plus x2 squared minus 6, you'll be less than 0. So all your blue points will be around here, and your red points, they are going to be around here, And look, I've got perfect separability in one dimension. Okay. And so, we can get now E in close to 0 and a DVC of just 1. Okay, one feature, one DVC of just, actually DVC is 2. That's the tightest possible link we could ask for with respect to linear models. Okay, and at this point, I'm going to say, I smell a rat. Okay, and it's very important for me to pause the video, or for you to pause the video and figure out whether you smell that same rat. It's a very smelly rat, and it's very important that you smell that same rat and sort of figure out in your mind, you cannot do this. Okay, and why can't you do this? You can't do this because you're not allowed to look at the data before you pick your feature transform. And, all of these sort of scenarios, which are are saying things like, there's this way to choose the feature transform, there's this way, but there's this optimal way to that one dimension. Those are all based on sort of looking at the data and saying, oh, there's a circle. You're not allowed to look at the data. Fundamental. You cannot choose your feature transform after you look at the data. You have to choose your feature transform before. Okay? And so let's discuss how you can actually use the feature transform in practice, because isn't the feature transform supposed to get you E in close to 0? Okay? So using the feature transform. Now, okay, so choosing the nonlinear feature transform, you have to choose the nonlinear feature transform before you see the data. So you must choose the nonlinear feature transform phi before you see the data. That's very important. But then you might ask, well, how do I even know I need a nonlinear feature transform if I don't get to look at the data? So this is where you have to sit down and think about the problem. So you sit down, you say, okay, I've worked hard, I've incorporated saturation, I've constructed the right features, but, it could still be that, even though I've constructed income, maybe it's income squared that is important. Or, I've got age, but maybe it's age or the square root of age that's important. Okay, so you're thinking that even though I have my features, I'd like to put in a little bit of added flexibility with some basically additional features that I get by transforming my original features maybe to the same original features plus a few more. That's an example of a feature transform that, strictly speaking, strictly adds features. Okay, so this is how you decide what's the nonlinear feature transform you're going to do. You have to think about the problem and say, are my features enough, or do I need more flexibility to manipulate those features, maybe multiply them together and so on and so forth. But then you come to the issue of, well, okay, so I need more flexibility. Then I have to sit down and think forever and ever and ever. Well, yes, that's ideal, but you could also instead just use some standard feature transforms that exist in practice. Okay, and the most standard of the feature transforms is the polynomial transform. Okay, so standard feature transforms. Okay, and there are many standard feature transforms: polynomial transforms, sinusoidal, i.e. Fourier transforms, radial basis function transforms, and so on and so forth. There are lots of different kinds of transforms. Okay, but you just need one. Okay, that can be your go-to feature transform when you don't want to spend too much effort. You've already spent effort collecting the features. Now you just need a little more power. Okay, and so what's the standard polynomial feature transform? So the polynomial feature transform. Okay, so let me illustrate it in 2 dimensions. So you have, your original input vector 1, x1, x2. Think of this as the original input vector in 2 dimensions. So I'm illustrating in 2 dimensions. Okay, so the polynomial feature transform of degree 1 is just to take your input and transform it. So degree 1, okay, is to take so let's call that phi 1, is to just take your input and transform it to what it was. I don't need a transform to do it. I'm just showing you that, this is the polynomial of order 1. So you have your 1, the augmented 1, and your 2 terms that you had before. Okay, what about the degree 2? So this is the degree 1. Degree 2. phi 2. Okay, you got your augmented 1. Now what you're going to do is you're going to have your linear terms, x1, x2, and you're going to have all the quadratic terms. That's why we call it the degree 2. Okay, so basically all monomials that involve your original dimensions of degree at most 2. That gives us the degree 2 polynomial transform. So we're going to have x1 squared, x1, x2, x2 squared. Okay, and so this is degree 2. Okay, and let's see. So here d tilde is 2, it's the same. So the VC dimension is 2. D tilde, dVC tilde is, 3. dVC tilde is 6. Okay, and now let's look at, phi 3. Okay, so that takes, my original input and construct 1, the linear terms, x1, x2, the quadratic terms, x1 squared, x1, x2, x2 squared, and the cubic terms, x1 cubed, x1 squared, x2, x1, x2 squared, x2 cubed. Okay, so this is the degree 3 polynomial transform for the two-dimensional original input. And you see that, what we have now is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9-dimensional space, and the dVC is 10. dVC tilde is 10. And if you want, you can go ahead and compute phi 4. Okay, and this is 1, the linear terms, x1, x2. Okay, the quadratic terms, x1 squared, x1, x2, and so on, up to x2 squared. And then you'll have the cubic terms, x1 cubed, and so on, up to x2 cubed, and then x1 to the 4th, and so on, up to x2 to the 4th. Okay? And so here you're going to have, how many additional terms? You're going to have x1 to the 4th, x1 cubed, x2, x1 squared, x2 squared, x1, x2 cubed, and x2 to the 4th. Okay, so you're going to have 5 additional terms. Okay, 5 in addition to the original 9. Okay, plus the 1 gives us a dVC tilde of 15. Okay, and you can keep going. Okay, and by the way, this polynomial transform exists for an original input dimension of also d. Okay, so it's the same idea. You take, the augmented 1, then you take the linear terms, then all quadratics, then all cubics, and so on. Okay, so we could define phi q, okay, is the polynomial transform of degree q. It's an interesting counting argument to ask. If you're in d dimensions of degree 2 for an original x of degree of, d dimensions. Okay, you can ask, okay, so this transforms into what dimension? And it's an interesting counting argument. You can go and show that the dimension of the space is going to be q plus d, choose q. Okay, so it's very rapidly growing with q, okay, especially if d is large. So that the dimension of the space is that minus 1. So this is d tilde is equal to this, and dVC tilde for a q order polynomial transform in d dimensions is going to equal just q plus d, choose q. So it's an interesting counting argument. I challenge you to go and figure that out. Okay, the point is that as you increase the VC dimension, as you increase the order of the polynomial transform, especially when the original dimension d is large, okay, you're going to get an astronomically large dVC, and you will lose control of E in versus E out. Okay. Now in 2 dimensions it's just growing quadratically. It's not as bad. Okay. In d dimensions it's growing polynomial in d, q to the d. Okay. Now, so what's my recommendation? So you think about your problem, okay, and if you think that you need a little bit more flexibility, well then I would suggest go to the quadratic nonlinear feature transform, the degree 2 polynomial transform. Okay, if you really want more flexibility, go to the 3rd order polynomial. Now let's go back to the problem that we had at the beginning there, and let me show you. Okay, so if I went into the polynomial transform, it was kind of magical that I said, let me ignore this, and that, right? I said, earlier I said, let's go from, x1, x2, I said, let's go to 1, x1, z1, z2, which is equal to x1 squared equal to x2 squared. Now that was just for illustration, but how did I know to ignore the linear terms and to ignore the cross term in the quadratic? You would never know that, okay? So you just need to make the decision, I need to go to the second order polynomial. Linear is not good enough. Okay, so if I go to the second order polynomial, then I must use the full second order polynomial because I'm not allowed to look at the data, and then that's what we get, okay? And it's quite nice. It's an ellipse. Generally it's an ellipse, and I've gone into this second order polynomial space. And, that's a reasonable fit to the original data. Okay. But, important, under the hood, behind the curtain, okay, behind closed doors, the client doesn't know. But all you're really doing is using the linear model in this, more complex space. Okay. Now, I just want to show you that, we have here in the polynomial nonlinear feature transform, we have here a real monster. So you have to be careful, okay, when you use this polynomial feature transform. And let me illustrate with this example. Okay, so here's remember I showed you earlier 2 cases of non-separability, and this is the one where we said, well, here it looks like linear, so let me tolerate the error and use pocket, and I'll get 2 errors, en of 2 or 2 over n, and my e out will be nice and tightly linked to en. So you might think, well, I'm not happy with that. And I learned about this tool called the nonlinear feature transform, and I'm a strong computer scientist. I can handle lots of computation. So let me use the 4th order polynomial transform. Okay, so let me show you what happened. Well, now having learned the theory, we know that you're going to have to pay the price in DVC for this small number of data points. Okay, and sure enough, when you go to this 4th order polynomial space and fit and then, do the inversion and see what does the decision boundary look like in your original space, look at that. Okay. Perfectly fits the data. So En equals 0. No doubt. Okay. En equals 0. Okay. But so what? You've lost control of En versus E out. And that's what that shows. Now you don't need fancy complicated VC theory and all that to look on the right picture and say, that's not going to perform well in practice. It looks like, have you overfit the data? So I'm throwing some language at you that we will learn about later. But, you don't need sophisticated theory to look at that right guy and say something is wrong. What is wrong is that you don't expect that guy to perform well in practice. And the theory says that as well, but has a very, very quantifiable, precise reason for why. You've gone into a huge dimensional space, and you've lost control between E in and E out. E out is no longer equal to E in. You don't expect that guy to do well in practice. Okay. So, on the left is our sports car, the linear model. Okay. Think and use it. Think because you need to construct the right features, and then use it because it gives you the link to E out. Okay. And if you can get E in small with the linear model, you've solved your problem. You have succeeded. Okay. If you think of the linear model as a sports car, the nonlinear transform that you put on top of this linear model is like a monster truck. It's like a truck. It's like an 18-wheeler. Okay. It's a huge monster. Okay. And with that monster comes a lot of momentum. And that momentum is very hard to stop. And as you can see, it's just going to go ahead and eat up all the data and fit it all perfectly. Okay. And you need to be very careful before you decide to go to the high order polynomial transform. Okay. It's very hard to break that guy. It's very hard to rein it in, and it goes and does that wild stuff. Now, you might wonder, is it possible to get this monster power of the nonlinear model, okay, but still not succumb to that, weird classifier that pops up that albeit fits the data, but I don't expect it to generalize? Is it possible? Well, so can you, have your cake and eat it as well? Can you have the power and not fall into that quote-unquote overfitting trap? Okay, now overfitting, we haven't studied this thing. It's language that we're going to see later on. Advertising. Okay, we'll have to, and we'll have to deal with issues like that because you have picked your polynomial transform before you look at the data. Okay, so what if you picked it wrong? Can we still survive? Okay, then we need more sophisticated tools. We'll study that later. Okay, for the moment, I just want to end by showing you the digits data, okay, and making a plug, okay, giving you an advertisement. Okay, so, if you look on the left, we see the linear model. Okay, and it does pretty well, but it gets a in-sample error of about 2.3, 2.4%. Okay, and then the out-of-sample error is comparable. Why? Because it's the linear model in 2 dimensions. You've got a tight link between E in and E out. On the right, okay, what happens if you go to the third order polynomial? Well, you get a much nicer looking fit. Okay, but that's fine. That's good. Okay, much nicer looking fit. And because you have enough data, you still have control between E in and E out. Okay, and you improve the performance by, maybe 1%. Okay, and, and because there's enough data, that percent translates into out-of-sample performance. So E out is close to E in. So when you have more data, you can afford to be a little bit bolder and maybe go to the third order polynomial. Gives you that little bit of extra flexibility to get E in small. Okay. And then you're wondering, wow, we did all this work. We've done like 6 weeks or whatever, 4 weeks of this course, 6 weeks of this course. And, we just got a 1% improvement in the error. So what that means is that, my accuracy went up from something like 97.5%, okay, to 98.5%. Big deal. Okay, I did all this, mechanics of the nonlinear transform and this and that and choosing features and all I got from going to the nonlinear transform is 1%, a mere 1%. 97.5% goes up to 98 or plus change. Is it worth it? And that's the nature of machine learning. Okay. And in general, solving problems like this, you can very quickly, with simple models, just intensity and symmetry, and the linear model, you can very quickly get very decent performance. And that's what I meant by if you cannot more or less solve your problem with a linear model, you probably didn't understand the problems. You can very quickly get decent performance, with not that much effort. Okay, and then the expert comes along and puts this, these finishing touches, okay, to get you that extra percent. Okay, and given that you're already pretty high, there's not much room to improve, but that extra percent, it's sort of a diminishing returns. You put all this extra work, you get an extra percent, but that extra percent is worth it. Okay, because if you think that, there are 300 million people, and if on average they send a piece of mail every day, let's say a piece of mail every week, or all that junk mail that's coming, it has to be sorted. So you have to read digits, okay? And there are 5 digits in the zip code. So 300, let's say 300 million pieces of mail a day times 5 digits, okay? That's 1.5 billion. That's 1.5 billion pieces of mail a day. That 1% improvement, okay, makes sure that a lot of mail doesn't get lost. So this small improvement is worth it when you're dealing with big numbers. And that's the nature of the game, is that you get up here and then you put a lot of effort to make small improvements. Okay, and those small improvements are where all the real money is. Okay, think about credit approval. So you've got your people, and you've got your clear approved. Okay, you've got your clear approvals, and you've got your clear rejects. Okay, and now you've got your borderline guys. Oh, these are X's, sorry. Okay, and now you've got your borderline guys, these guys. Okay, and these guys. Okay, and all the money is made in the borderline, believe it or not. Okay, because the clear rejects, no problem. Anyone and their mothers are going to reject, and the clear accepts, no problem. Anyone and their mothers are going to accept. And you don't make money off those guys, because if they're going to pay off their loan, okay, good, they paid off their loan. They're not going to get a loan, so I don't make or lose money. But this borderline are the guys who pay off lots of interest and so on and so forth. So getting that extra percent of accuracy back from the linear model, which would do this, if you can do the nonlinear model and do that, okay, you get these borderline guys who are going to pay off a lot of interest, and those non-borderline guys you reject who are going to lose you money. And now that's where the money is to be made. So that 1%, don't laugh at that extra 1%. Okay, that's all I'm saying. Now, I'm going to make a plug I'm going to make an advertisement for the linear model. So we're done talking about the linear model. Okay, I'm going to say it one more time. Not that I haven't said it enough, but I want to end this lecture at least saying it one more time. Okay. So the linear model is the first thing you should try. Or at least when you approach a problem, you should say to yourself, I'm going to try to solve this problem with the linear model. Okay, it works in practice, because if you think about the features carefully, you will get a good in-sample error, and then the linear model takes care of the E out to E in link, and so you will get good out-of-sample error. And I'm even willing to challenge anybody out there. You think you need a sophisticated model? Come, bring your data to me, bring your problem to me, and odds are I will be able to get a pretty decent solution with the linear model. So if you cannot do it with the linear model, you haven't thought enough about the problem. Think more about the problem. Now, of course, we have the linear model, and we have even the ability to tolerate error with the linear model, the pocket algorithm. Okay? But we also have this additional power of the nonlinear transform. But be very careful when using the nonlinear transform. You have to pick your nonlinear transform before you look at the data. Okay? So you have to choose your nonlinear feature transform before you look at the data. Always, 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 always. If you want to be able to say something about E out. If the only thing that matters is E in, you can do whatever you want. But if you want to be able to say something about E out, you have to choose your nonlinear transform before you look at the data. Okay. Linear model, I'm plugging it. It's fundamental. Okay. And as I already just described, in its own right, it's fundamental for solving problems. But even if you decide to go for more complex models, they are the building blocks. The linear models are the building blocks of these other models. Use the linear model and realize that it's worth getting to know the linear model very well. Make it your friend, your best friend. Okay? Because when we study neural networks, when we study support vector machines, we'll be digging back to the vault of the linear model. And let me just mention that everything I said today about the nonlinear transform, okay, it doesn't rely on the fact that we're doing classification. So you can use it for regression and logistic regression. The mechanics is exactly the same. You transform your data, okay, and then you use the linear model for whatever problem you're trying to solve in that transformed space. Okay, so if it's logistic regression, you minimize the cross-entropy error using gradient descent. If it's regression, you just have the one-step pseudo-inverse algorithm. In all those cases, what comes out in your nonlinear feature space Z is the weights W tilde. And now you want to apply your weights W tilde to a new test point. You just transform that test point and apply W tilde in that space. Okay. So, very powerful linear model. Use it. Checking out.